I would like to welcome everybody to today's webinar, Modernising Ground Sites for Long-Term Success. I'm Richard Hooper, publisher at the Satellite Evolution Group, your moderator for today's event. Now, before I start introducing the panelists, I would like to mention a few housekeeping details. There is a question function that I would encourage you to use, so please ask questions throughout the session. We will try to answer all the questions, time permitting. And if we can't answer them all, we'll follow up afterwards, after the event. And should we lose a speaker, we will continue and restore their connection as soon as possible. Now, let me start introducing the panelists. We have with us today Matt Langenbahn, Senior Vice President, Kratos Space. Matt plays a key role in the digital transformation of satellite ground systems at Kratos. His team collaborates with the product management and engineering teams to build next generation ground system solutions. And we have Brad Bode, Chief Technology Officer, Atlas Space Operations. Brad brings over 23 years of software development experience in the aerospace industry to the Atlas team. As the architect and visionary behind Freedom Ground Software as a Service, Brad is responsible for hundreds of thousands of successful satellite passes and terabytes of data collected. So let's get started. The softwareization of the satellite industry has been happening for a while now. In the last decade, many satellite operators and service providers have at least adopted digitization of RF over IP transport to solve various problems they faced. What is your perspective on the status of the satellite industry generally in moving from hardware to software, also known as virtualization? Let's start with you, Matt.
Yeah, it's a great question, and it's been about a decade we've been working on this. The way I would characterize it today, you're right, we're right past that tipping point, I believe, where there's enough industry impetus and standards-based that people are starting to rally around a virtual ground system as being the de facto going forward. I remember working on this 10 years ago, and when we first started doing digital IF transport, and several respected labs and FFRDCs were telling us that's not possible. There's no way to get past that point, but we believed it was, and we started working on it and partnered with to prove its viability at the time. And what really got us past the tipping point is not that technology itself, but the overall improvement of network reliability, bandwidth, and compute power. As that has increased over the last decade, it's become more and more obvious that virtualization and digital IF is the way to go. Once you got past that digital IF transport, and then it just opened the aperture to other technologies and being able to virtualize the rest of the applications, because then it becomes obvious that a modem can really just become an application. It doesn't need to be a piece of embedded equipment with an ASIC or an FPGA processing anymore. And we're well past that tipping point now. And I think now you're seeing people just deal with it on an economic basis and looking at digitization as a capitalization problem. As old ground stations need to be refreshed, or as new programs go up, a software-defined ground is the way to go, or a virtualized ground, excuse me, is the way to go. It's just becoming the way you build ground systems.
So Brad, what's your take on that?
I mean, there's definitely a lot to say on this topic, and I'm going to jump back 10 years like Matt did. And I don't know if you remember, Matt, but we did a test with Kratos with the Q radio in its early infancy, downlinking a NOAA satellite pass, digitized going into the cloud. So we set that test up, and that was actually one of the first things Atlas did that ended up winning the NOAA contract, which we've had for many years at this point. So we were looking into how to virtualize and looking for partners with how to virtualize the ground systems at our inception, because we started as a cloud company, software company that really wanted to streamline operations, and we're streamlined the RF chain as well. And I think that's one thing that can't be understated is how the virtualization of ground systems has made it such that we can be nimble in our approach. Having cables and wires plugged into each other makes things not nimble. So when the RF comes into like a wideband spec net, and the spec net can distribute the data over IP. The spec net is the thing that digitizes. It distributes the digitized RF over IP. Now we have a lot more flexible ground system, not to mention that the wideband spec net allows for us to remove or redundancy in the RF chain, remove some of the extra components that now the wideband spec net was able to handle, like down converters. So just simplifying the RF chain at the ground site and having less parts introduces or reduces the risk for us as a company that continually operates those. So virtualization has its benefits to the operators of the ground stations, but that trickles, well, not trickles, but it moves upwards. It provides benefit to our customers because now our customers can move faster and have a better quality of service because we're able to adjust quickly to their needs. And that I mentioned the wideband SpecNet, but that goes for the Q radio or all the quantum line or the QMR. All of the products that deal with digitized RF can now be easily moved around, whether it be in the cloud or at the ground site. Now, I'll mention that you would think that the biggest benefit is digitized RF into the cloud. It's not always the case because guess what? A lot of the locations on Earth don't have high enough bandwidth to actually send the digitized RF into the cloud. But the benefit is still local at the ground site, being able to have that nimble RF chain. Hopefully that answers the question. It's really about simplicity and quality of service to the end customer.
Yeah.
Agreed.
So, Brad, Atlas is a pioneer in softwareization. I love that word, of satellite ground systems. A few years back, you faced some challenges that ended up being the beginning of a modernization journey. Can you share with us what some of those challenges were?
Sure. I mean, first, I'd like to go back maybe 8 years, just to say the biggest challenge at that time was convincing investors that the ground was important, which is probably seems very obvious to the people on this call. But at the time, everybody was investing into satellites, right? And that was the sexy thing to invest in. And ground has since become extremely important in the industry. I think it's had its comeuppance. Everybody knows that it's the pipeline to Earth, and it's extremely important. So that was one of our biggest challenges. And then when you talk about modernization, we have to just first admit that maintaining a global network is extremely difficult. And it is more difficult if you are dealing with, physical hardware that can't be updated as frequently, where you might need to actually physically be there to flash firmware and things like that. Now that we're on VMs, virtual machines, it's much easier to update in a timely manner. So knowing how difficult that is on a global network, you need a bunch of other things, which Kratos has definitely helped with. We need easy rollbacks, the ability to roll back software if something fails. That's something that is extremely important to us, and that's worked well with Kratos. We need consistent builds across versions, and Kratos has made a lot of effort in making sure that they're non-breaking as we move from one to the next. These things sound boring, but I can't emphasize how important they are for, again, quality of service to the end customer, because that's the most critical thing. And then and one of the most important ones to us was also having consistent APIs that maintain their endpoints across versions, and modern APIs, REST APIs that are responsive, but also consistent and easy to integrate. Again, that sounds, commonplace and trivial, but it's not as much as you think. It's hard maintaining APIs and keeping them consistent because for us, downtime is money. And so every minute we lose to, figuring out a problem or some endpoint or some API that's changed is time on an antenna.
Well, taking up on this point, let's turn to Matt here for a minute. What are some of the things you have been seeing in the industry and from customers that is driving product development at Kratos? Now, I'm going to pull up a slide that you can use here, Matt,
Right.
and
Right.
You can start explaining.
Yeah, you bet. It's interesting. That question builds very nicely off of what Brad was just describing on the challenges in building his network out. So it's worth spending a minute. This slide illustrates it really well, as simple as it is, what it's really about to digitize. So the top layer there is just showing RF transport over digital IP. That's the very first step we did a little over a decade ago and prove that viability in the marketplace. So once you have that digital transport, you can see the next one down. It makes it easy to move to, well, why would we ever convert that back to analog? Why don't we just design our modems to ingest that digital IF? You've effectively cracked the modem in half. If you go back to how modems are usually made, there's a digitizing front end that digitizes the signal from the antenna and then does the processing. In that second line, you can see basically cut the modem in half, and now you can push the digitizer out to the antenna and make that really efficient. It really limits the amount of analog RF distribution you have, which can be clunky and hard to maintain, and turn it into digital signals. And now you're dealing with network transport and more of an IT problem downstream, which is a little easier to deal with remotely. And to Brad's point, it's easier to get commonality in your ground system. Now you can start to standardize on equipment and use more commodity and standard-based systems or transports or network switches and things like that. And then the last slide at the bottom there shows how you don't have to run the CNFs distributed from the digitizer. If you have a remote site, and ATLAS, for example, it has a mixed mode. Some of the sites are easy to access with good network bandwidth, and some of them are in really terrible locations because that's where you can talk to the satellite. But you can move that edge cloud out to be close to the antennas and still do all your processing there and just bring the baseband data back when it's convenient. So, the first thing we had to get past on this, like I talked about before, was feasibility. You had to prove that this was all possible. And I love that Brad referenced that demo. Yeah, I remember it. I remember us setting it up. That's the first time we ran that radio in a cloud over a live satellite operation to prove feasibility. So ATLAS and Kratos were linked up there, and that worked really well. I think the very last note I'll make on what I'm seeing also builds on what Brad is saying is this type of network for satellite control and that mission downlink management, it was usually an afterthought driven by the satellite. People would build satellites, design their payloads, and build their ICD for communication, and then they would build a ground system matched that satellite and operate that ground system for that satellite. There's been a massive proliferation of different missions and satellites going on orbit over the last decade, and the economics didn't work anymore. You can't build a ground station per satellite anymore. It's a crazy thing to do. So that really led to a rise in demand for as-a-service applications to be able to say, I'm worried about my satellite and my mission. I just need the ground to work. And that's where ATLAS add value, just making the ground work so we can control the satellite and get the data with more common approaches and common infrastructure, and not building a purpose-built bespoke ground station to satellite. So ground is becoming much more general purpose and supportable, which allows us to make things like our radios and the quantum product more of a standard product and be able to test and regression test and stable APIs and all that goodness that Brad mentioned. That's an overall industry evolution, and it's working pretty well.
Brad, what was the scope of the modernization project ATLAS embarked upon? What were you looking for? Brad, sorry, Brad, you've on mute.
It's a great question because there are so many aspects of modernization, and in some ways, we were when we started and up until this day almost too modern because and I'll tie this all together, but we were integrating the cloud with ground stations in 2015 and running all the data through the cloud. And none of our customers have access to any one of our ground sites. They go through something called the Freedom Pass server in the cloud, which multiplexes or connects to any ground site securely. So there's a lot of aspects that were very modern that we do. And that's why we call ourselves ground software as a service, because there's a lot of capabilities that we layer on top of the infrastructure. So when we talk about modern, we were too modern in one area, and then modernization at the actual ground sites is what we're talking about here. The hardware is hard, and it takes time to catch up. So modernization at a ground site means having ground infrastructure. We wanted a solid base of working, tested features with high quality documentation, consistent APIs, as I mentioned before, and cost is a factor, right? The number, this is one of the keys, and I think Matt just mentioned it. It's the number of baseline features, mod cods, modes that reduce. If you have a lot of those features in just the baseline, you don't have as many requests for modifications because, as Matt knows, he gets a lot of requests for one-off work that they have to make the choice. Do we roll it into the product and make it part of the larger picture, the larger product offering, or do we just do this one time? And as any good software person knows, that's a difficult decision to make because there are costs associated. But I will say this, Kratos has done a great job of covering the 90% case. We almost never get a customer that comes to us and asks for a particular capability that Kratos doesn't offer. And if they're using something outside of that 90% case, we try to steer them otherwise because usually there's not that good of a case for it. It's very rare that we encounter that. Now, this map that you see up on the screen illustrates the breadth of our network. We do run every major antenna vendor. We have integrated. We've used 30 different pieces of hardware across the board to deal with the RF chain. But from a modernization perspective, as I said, those consistent APIs and consistent data formatting coming out of the modems and the hardware. And again, Kratos has made major efforts in consistency since the Q Radio first launched. And I think the key phrase here would be one-stop shopping. So I can go to Kratos, get low rate TT&C, and I can get high rate, and I don't have to mix vendors. It all comes in one package, and the products seamlessly work together. So from the perspective of modernization, it really goes back to what I said earlier, which is having a nimble ground station, the RF chain at the ground or at the ground and in the cloud, so that I can serve the customers better. And that's exactly what we've done. It's made it easier for us to operate, and the consistent APIs make it easier for us to do root cause analysis, to pull metrics for every pass, to have automated, pass validation. These things are critical for operating such a large network. And Kratos has been there.
Well, you talked a lot about Kratos there, Brad. So I'm going to come to Matt now. Can you talk us through how Kratos worked with Atlas on this project and the basics around what the solutions were provided? Now, we've got 2 slides here. I'm going to put them up on screen and I'll let you talk through it, Matt.
Yeah, so there's been a pretty long legacy here, as Brad was indicating. We've been working with Atlas since they first started conceiving and prototyping some of these things. And it was really a very happy coincidence that here at Kratos, we were starting to do our virtualization push and move more to software-based and digitization. Right at the same time, Atlas had the very same vision. We met each other and started talking, and it was very harmonious. It was good that we met each other when we did, because the visions aligned very nicely, and we've seen some of that play out over the last 10 years. So Brad referenced the early demo we did. This slide illustrates it pretty well. So this is the wideband mission downlink slide, but it looks pretty much the same for TT&C. What we effectively did with Atlas in that very early demo was to use a SpectralNet, a product we still support today, and connect it to an antenna and then remotely send those IP packets. It was all the digitized RF to the cloud, where we processed it with our radio. The radio was only a couple of years old at that point when we did this over a decade ago, but that was the first use case example where we took a live pass from a satellite and showed that we could successfully close the link, demodulate the data, and get the baseband data available in a cloud. It was a very important point. So I think ultimately why Atlas works so much with us over the years is because of that shared vision and building off that one data point with the demo. Really, Kratos's core contribution is we're a leader in signal processing in the radio and the FEP. So Brad talked about that a little bit with our product. We make a focus to try to build a full-featured radio that will solve most mission cases by itself. And he's right. We face this decision all the time where people still bring us unique requirements, and more often than not, we're able to work that into the base radio product itself, because it's getting to be less and less common where if someone asks for something unique, that more often than not, someone else will ask for it on follow-on programs, and they become industry standard features. So this is the best way to approach that. Working with Atlas over the years has really helped us get that learning because of their customer engagement. Now it's funny, a lot of times we don't even know who their customers are. Atlas will come with us and say, we're onboarding a new customer, they need this type of processing. Being a software-based system, we can turn that pretty quickly and get an updated app out, which Atlas is then able to push out through their managed virtual machine structure to the field pretty quickly and deploy. So we've learned a lot from each other over the years. We get that consolidated point of input from all their customers saying, here's what we need, here's how we're moving forward. And we can focus on the technology and the signal processing and make it all work and rapidly update the product to support them. The last note there, what we really learned working from Atlas is the importance of not just those individual components and being able to run them and have them do their individual missions, but as Brad was starting to allude to, the orchestration of all this and the variation from contact to contact and the different customers trying to use the antennas, the orchestration of that and the configuration and managing all that is a pretty complex undertaking. And so both Atlas and Kratos have focused on that over more recent times on how do we keep this clean and orchestrated in the configuration management, the customer requirements on the use of the network. It's a complex task, and it's taken a decade to get there, but it's been a really interesting journey. And I think both companies have learned a lot from each other. It's a good relationship.
Well, you talked about the complexity there. I'm going to go back to Brad a bit here. As you moved forward to implement these solutions at the different ground sites, what was the process like? Were there any challenges or anything that surprised you about it?
Well, you know, in truth, we've been working with Kratos for so long that there weren't that many surprises. Um, there, the challenges are always there, and I'd say that some of the biggest challenges are making sure that, and it has nothing to do with Kratos. It has most to do with maintaining a global network, making sure that you don't have downtime on that network, that you plan for these network updates uh, as much as possible so that they are not, pardon me one second. And really, when you start to move beyond, the problems with just maintaining customer service, we start to look at where the problems arise when it comes to uh, like just designing a system that is scalable. So I didn't mention scalability in the modernization effort, but um, we want to make sure that we can deploy quickly and that we can provide that foundation for expanding the network quickly and easily, but maintaining that quality of service. I know I've jumped around a bit here, but the the issues that we encountered were far and few between. It was more so the planning of the effort um, had to be perfect, and it had to be make sure that our customers were not affected by it. So, you know, we actually have to look for slices of time that our network has room, you know, between passes to actually update. And we might have to do that in a span of, you know, 10 minutes. And having virtualized systems allows us to do that. So, you know, biggest issue is probably that. It isn't we relied on Kratos to deliver something that would be consistent and quickly installable. And that has remained. And we've been working with them so long that we didn't expect any issues there. I jumped around. I hope that makes sense.
Yeah, I'm just going to ask Matt, was it as plain sailing from the Kratos side?
Well, I'll echo what Brad said. There weren't a lot of unexpected things, but it is hard work. Yeah, the problems we solve aren't trivial. So I'll talk more from just generic. How's the overall satellite industry and this type of network like Atlas? How has it evolved? Really, the things you had to deal with is a little bit of what we touched on already, just the variety of missions and all the different companies trying to fly satellites, this rapid rise we've seen, and we used to call it small sat. Now it's just proliferated LEO or non-geosynchronous orbit type programs. And it's really, I think, gone faster than anybody anticipated it would 10 years ago. I mean, even if you take SpaceX's Constellation out of the equation, there's still more satellites flying today than anybody anticipated there would be 10 or 15 years ago. So the thing that was surprised and challenging is dealing with all these new players in the space market and the variety of missions and how you can satisfy all that. Again, I mentioned this earlier, but you know, if you went by the model from 20 years ago, there's not enough real estate on the planet to build ground stations to talk to all these satellites. Of course, I'm exaggerating a little bit, but it's an economic problem. You just couldn't do things the same way anymore. Atlas really had the vision and came into being at the right time to match that rapid rise in satellites on orbits and the need for all these contacts, which also drove a lot of industry things, which Kratos believes in and is our vision around more standards-based deployments, more productization, more commonality at ground sites. you know, when NASA first started throwing satellites up, it was a research project, and it was cool to be different and experiment with new mod cods and new signaling and trying to save a little bit of bandwidth for efficiency. And that's not what's driving the industry anymore. People just want assurance of connection, and they just want their data. And the experimental phase of ground systems and space to ground is over. It's becoming business and economics. I need my data off my satellite to pose my business case. Can you help me do that? And that's been the focus of Kratos and Atlas as well, is yeah, we can close a link with your satellite and get you your data. You don't have to run a science experiment to build a ground station. The technology is well proven. We're refining it into something that's repeatable and supportable and secure. So that's really what's happened over the decade of this partnership here.
So going back to Brad, what was the importance of the virtualized ground sites when it came to the development of your network management solution?
Well, just in general, you know, we touched on this earlier, having virtualized ground sites, the importance of it is keeping it nimble. You know, we have an example where one of our customers was, you know, they were already on our network. They were not using UHF at all, and they were using X-band. And one of our customers needed immediately, as quickly as possible, to be able to use UHF. This was due to a LEOP concern. Something dropped out, something was failing, and they approached us. It was a week before LEOP where they needed UHF, and they had never integrated with the UHF. So as a testament to our software, for us, it was just, okay, we'll open up that new site for our customer. So we gave them permissions to access that site. And what that means is it just allows them to see the site in our API, to task time on it, and we multiplex again and deliver the data to them through the cloud. But then now that's one half of the equation, just providing that access. The other half is we've never worked with this customer with UHF before. So then we asked, well, do you have, you know, configurations for Kratos by any chance? And they did. And it was a matter of just plugging in those configurations, routing the digitized RF to the correct modem, because we already had a wideband, or I think it was a narrowband receiver, you know, SpecNet at the actual location, and connecting those two, not with a cable, but with digitized RF, and then beginning testing. And so that took, from the time they asked us for access to the time we had configurations, it was hours, and we were testing. And then a week later, we successfully did a LEOP. So there's no more real world example of what it means to have a virtualized ground site than that. There were no cables that needed to be plugged in. There were no, you know, RF changes. It was as simple as a configuration. So virtualized ground systems really just help, again, be nimble, respond to customer requests. And if it was the case that mod cod wasn't supported, we know that we could also go to Kratos and say, hey, consider supporting this. You know, they couldn't do it in a week, but maybe they could do it in 3 weeks, and we can deploy remotely from the cloud all the way to the ground site without affecting anything in that RF chain, without having to needing any physical presence at the ground site. So this cuts down on risk, it cuts down on labor, and just makes an overall better experience for our customers.
What intrigues me about this, and you know, I'll let you both answer this, but we'll start with Matt. Digital opens the door to the importance of security in the network. Every day we read about networks being breached. There is nothing more important. How are you achieving this?
Oh, this is a great question, and I'm glad you brought it up. I was sitting here kicking myself for not bringing up security more in the previous questions. It really is important. I mean, again, if you go back 20 years and look at how ground stations were built, I hate to say it, but a lot of times security was more of an afterthought. It was, Brad said earlier, hardware is hard, but space is hard. It's really hard to close a link to a moving satellite in orbit and get reliable transmission and data connection. So in previous decades, that was so hard. You didn't worry about securing the link too much because you could barely do it if you had all the insider knowledge and you were intended to do it. With the whole proliferation of different satellite programs and maturity of the technology, that's not the case anymore. It's now a lot easier for a lot of different groups to contact satellites or get into networks that they shouldn't be in. And not only that, there's a lot of worries about accidental interference or crossing streams. So security has grown and grown in importance, and not just for government applications. Anybody who's flying satellite, there's so many new companies making a business off of missions performed from space, whether it's sensing or taking pictures or gathering data or relaying communications. The private industry business cases for space have exploded in the last 10 years. And all of those companies, if you're a government program for DoD or civil, or if you're industry, you're now concerned about security. What we've seen happen is space is no longer this unique realm of science and astronauts and PhDs. It's just another layer in the information grid for the planet, for terrestrial networking. It now extends up into space. And so you have to treat it that way from a security point of view. It's a big deal. Again, if you go back in time and look at how ground stations were constructed prior to virtualization, it's a rack full of embedded equipment and specialized RF gear. Usually each one of those rack units has its own embedded processor and operating system, and you couldn't abstract those away from each other. You had to send someone on site to do security patches or update OSs, make sure the network was secure, and it was difficult to maintain security. For the same reasons you get the rapid upgrading of capability and remote supportability, you get those security benefits from going virtualization as well. And at Kratos, we've made a distinct effort to abstract away the processing applications, our radios, for example, and abstract those away from the OS and the underlying hardware so that each one of those can be maintained, updated, and held secure individually. So it's much more like software-defined networking on the ground based on commodity hardware and cloud applications. And you can push security patches, you can do the testing. It's another case where having common products with common APIs and regression testing helps, because we're able to supply security patches both at the hardware and the OS layer, but we also do a lot of testing of our applications for security. And that's part of a normal test before we deploy anything to the field. By abstracting those layers away, too, it allows you to close a critical OS patch, for example, without a massive disruption or sending someone to site. In Atlas's case, you can, if you have 15 or 20 minutes of downtime between scheduled passes, you could do that upgrade on a virtual machine, get it installed and ready for use on the next uplink. So security is a big deal, and it's growing in importance, and industry is making it a requirement, and the whole customer base, not just industry. Security is a must for these type of networks. And I'll tell you, if we hadn't gone to virtualized and software-based type of architecture, security gets very difficult to maintain with what's honestly becoming more of an antiquated type of architecture. It's almost impossible to keep those old ground systems up to date. It just requires way too much effort, where it gets to be just a normal course of business when you go to the softwareization of ground.
So Brad, I mean, you're right in the middle of this network. What's your take on the security aspect and what are you seeing?
Yeah, not just, I mean, we're in the thick of it in such a way that we just completed our NIST 853 at certification. So that means we were third-party audited for 1,200, approximately 1,200 security controls, which covers every aspect of our company in terms of our software. So all of the data movement through our software, how things are connected, what are the policies and procedures across the entire organization, at the ground sites, in the cloud. I mean, it's an intense 3 months of having someone look at every aspect of your software and your supply chains, everything. This goes well beyond NIST 800-171. NIST 800-171 is primarily what the government is looking, the US government at least, is requiring operators to have. But if you take a look at it, from a bigger picture, if you picture kind of an onion with different layers, security over time has kind of evolved. As Matt said, maybe 10 years ago, security was pretty much just the outer layer of the onion. It was the perimeter security. You only secured access to the hardware because all you had was hardware. So most of the hardware, didn't have to worry about security. That's changed. Today, from a security perspective, everything that talks together, that operates together, has to be secure. And even the OS that something is running on has to be updated. I'll give you a perfect example. In our NIST 853 process, we were prepared, but there's a thing called POAMs. And you don't want to put something in a POAM. But because that's a record of something that is wrong, but maybe needs to be corrected or can't be corrected. Luckily, we have almost nothing in our POAM, but you do encounter these instances because we own so much different hardware across the globe where something that is so tied to the hardware that cannot be decoupled from the hardware, that means updating the underlying OS or updating the firmware on that hardware can't happen without breaking something. Which means if there is an OS vulnerability, a documented one, which would be a CVE, that's what those are generally called, you are unable to upgrade that software that's running on this commodity or this hardware. It's not commodity hardware, it's custom design hardware. You're unable to upgrade it, or you or you break your system. So this is something that you don't want, in which virtualization comes into play here. As Matt said, they've decoupled from the hardware. So that means as a company, while they are working on patching their software, we can simultaneously patch the underlying OS that they're running on. And that is not always the case. I know it sounds trivial. It's not. And so the timeline for updating these critical vulnerabilities or any vulnerability is between 30, 60, and 90 days. So you might have, for a critical vulnerability, 30 days to remove it from your system. Otherwise, you're now relying on the perimeter security that wraps around the entire system, which ours is great, but to maintain some high-level security, you need to be able to update frequently. And in order to do that, you need to have that decoupling from the OS and really good software practices, frankly, to make sure that you're on top of it, that you're watching for those CVEs. And then I'd also say that where the industry is heading from a security perspective, it's not there yet, is zero trust architectures, where everything within the system, so we built an architecture. It's not just a piece of software. It's many pieces of software connected through a global cloud architecture. Now, what that means is every one of those pieces needs to be updated but they also, many of them talk together. And for zero trust architecture, we need to have authentication between these different pieces to make sure that if there is a breach beyond the perimeter, that someone cannot talk to any one of the individual pieces without authentication. Now, there are many, many ways to do that, but it's not quite a full requirement by the government as of yet, but it's coming. And so virtualization is going to make that easier because the software patches will start to allow for it. And these are the things we deal with when it comes to security. We need compliance that's centralized, it's auditable, and automatable, and that keeps pace with those cyber requirements. So it's difficult and very important, and I think increasingly important in today's age, where everything is ubiquitously connected to the network, and all it takes is one mistake, and everyone will realize how critical security is.
Well, before we move on to some questions from the audience, I'd just like to know about future-proofing. How crucial is the move to software ground segment in achieving future-proofing the network? Matt?
Yeah, for a lot of the reasons that Brad just articulated, it's similar to security. Future-proofing gets a lot easier when you're in a virtualized environment because of that same concept of abstracting the application from the OS and the network and the hardware itself. One way to look at it, it becomes more of a cloud-based or a traditional IT problem rather than a unique ground site. So again, I sound a little bit like a broken record, but going back a couple decades, it was really hard to future-proof a ground station when you had bespoke, custom-built pieces of RF gear and processing. To upgrade those, sometimes it was impossible. Sometimes you had to rip it out of the system, send it back to the original manufacturer, and they would modify it or augment it, retest it, maybe upgrade some parts and then send it back. And you go through a whole design and fielding exercise that could take a year or more just to update some capabilities on an existing ground site. So the concept of future-proofing, it's never 100%, but when you get to virtualization, and that abstraction I'm talking about, it allows you to maintain and upgrade your system in more of an OSI layer approach and look at the stack. So you can update the application or the OS or even the underlying hardware without disrupting the rest of the system, because you have those solid tested APIs and those interfaces testing. So that's what really allows you to get to a better state of future-proofing with virtualization. That's what happens when you try to say 6 words at once. The technology itself, it starts to look more like a modern IT infrastructure, which is constantly undergoing change. So that's one thing with virtualized ground. Just think of it, it's not a static thing that you build for this program anymore, for this satellite. It's now this ever-evolving system that you can maintain the layers in security and updating and compliance. And they're constantly evolving and upgrading. An interesting note on future-proofing, this is something we've learned with our high-rate modem processing, which ATLAS uses. We designed a totally virtual radio called the QRX that does the mission data downlink. It's a high-rate DMOD. And we specifically chose an architecture that relies just on the x86 processing, no acceleration, no other GPUs or other hardware accelerators. While that might be an odd choice, you can't quite go fast enough. What you get is you get the benefit of Intel and other processor companies' investments. They're investing billions and billions of dollars every year into R&D and to make those chips run faster. Same with network switches. And every time you get a new generation of processing or network capability, virtualized satellite ground systems now get that extra performance with very little effort. It's a requalification effort and retesting. When we saw Intel move from their Gen 4 to Gen 5 processors, we got effectively a 20% increase in our symbol rate processing and our wideband DMOD without any effort, really. It's just telling customers, oh, if you go get these commodity servers and install our high rate DMOD, you'll be able to get this much more symbol performance out of your DMOD. Those kind of things are what future proofing is really about. And it's about getting the synergies and taking advantage of other investments that aren't specific to space, just in general technology, network, and compute. And those investments are massive compared to what the space industry can muster to solve a problem. So that's how we look at future proofing. And another key benefit of going to virtualization is riding those more commonly used technology waves.
Brad, did you want to add any key points to that?
Yeah, I'll say that, aside from the stuff we've talked about, we've got, adaptation to new missions. We've got modular API-driven, interoperability. We've got speed of integration, security and compliance, resource elasticity, being able to move it and move resources around. I think that's probably the most important one for us, because, what Atlas does is we abstract all of the hardware away from our customers. They connect to us. They don't know or care what hardware they're connecting to. We're huge fans of Kratos, but it's a data management problem to the customer. It's where is the data flowing? Where's it coming from? They don't even need to know where it's coming from. Just get me my data when I ask for it. And that's going to be increasingly clear as we start to get more types of and more ways to connect to space. It might be optical. It's definitely going to be some form of potential space relay, but there's still data that needs to come down, hit the ground, and be distributed. As network bandwidth increases, we may want to shift some of those poor bandwidth locations, move those the modems into the cloud so that we can scale within the cloud and do DigiRF over a longer distance. That's something that we're definitely hoping to be able to do because the cloud scales pretty much infinitely. So future proofing really to us is about having the flexibility to be able to move some of this previously hardware-based software to the cloud and monitor it better, scale it better within the cloud. And then also make sure that we're prepared for the future where data streams can come from different sources. And that's why we have the Freedom Pass server, which multiplexes data streams. That's why we have one API for all of the different antennas that we have integrated from AWS to Viasat to ours. The future's looking bright. So,
well, I'd like to thank you there, gentlemen, for those answers, but we've actually got some questions that have come in. So let's take this first one. With digital IF, what is the plan for data distribution over network? Cloud rates will skyrocket with digital IF, and how would digital IF with the cloud work for ranging needs? Now, I don't know who wants to answer that one.
I'll be happy to take a crack at that. So distributing digital IF over network is a challenging problem. And as Brad was talking about, it's not the same at every site. It really depends on the network availability, where the antenna is at and where you're digitizing. So for sites that are near good network access, where you can get plenty of network bandwidth, it makes a lot of sense to pull that digital IF to a remote cloud somewhere or to backhaul it somewhere. And honestly, it doesn't make a lot of sense at very remote sites where you have spotty or only narrowband network connectivity. There absolutely is an expansion factor when you digitize RF. You can take the bandwidth of the occupied spectrum, and depending on how many bits you want to digitize for the quality of the signal, you get an expansion of 5 to 10 to 15 times that bandwidth number into network bandwidth. So digital IF, if you want a wideband signal and a very good signal quality, it does take quite a bit of network bandwidth. And those are considerations you have to take into mind. There's no one size fits all. You have to look at and kind of pre-plan, where's my antenna, where's the closest network trunk I can connect to, and can I get 100 megabit, 200 megabit, even gigabit reliable performance across that. So you have to understand the network and the physical locations a lot to make those determinations. The ranging needs question is the second one. Ranging is all about timing and deterministic timing. And it's a great question. It means someone's paying attention here. Ranging depends on very precise measurements in signal to satellite and back down to nanosecond type resolution. To be able to determine where a satellite is for positioning. And anybody who knows a little bit about networking knows that you have sometimes dozens of milliseconds of jitter on a network link. So how are those two compatible? There actually are ways to solve that problem, which took quite a bit of R&D on our part, but our ranging solution is pretty solid. Ultimately, you have to timestamp the data and maintain that integrity of the signal right when you digitize it, that analog to digital conversion. That becomes your source of truth for timing information. And that timing information has to flow in those digital packets to the rest of the processing, so that you have a common time reference. It is a very complex problem, but it's one that we've solved and have been operational with for quite some time now. But it's a great question.
Well, I have a question here for Brad. How long does it take to virtualize a ground site, and what is the cost benefit ratio?
Well, how long is, if you're starting from scratch, you don't have customers on it, it's not that long, because you're just replacing a few pieces of hardware with maybe commodity, like putting in a Dell server. And the thing is, we already have servers at each one of our sites for our own purposes. So in the case of a site that has customers on it, it takes longer because we have to make sure there's no downtime for that customer. And that's where the difficulty comes in. Virtualization in itself is not that hard because, again, Kratos has been reliable with their product. And so we know that's going to work. It's finding the window to do it to disrupt the least customers as possible. And once you have that high powered or decently powered server, depending on if you're doing wideband or narrowband, it's a matter of plugging it into the stack, making sure that all the IP routing is there, testing it. When we install a new site, that part of the process could take us, 1 day. It's not bad. Again, when you're dealing with a site that exists and you're trying to upgrade it, that's another story, because you have to unplug things, plug new things in, and be highly coordinated in how you do that and efficient in your timing. So it's never that bad.
Well, we have another question here. I think we've got time for this and perhaps one more. You mentioned that the industry is moving towards zero trust architecture, but it is not there yet. What are the major challenges to achieving widespread adoption of zero trust? And how long will it take to get to that point? I'm not sure who wants to answer that, but...
Well, I'll take that. So one of the challenges is having a centralized sign-on and authentication, because each application is going to need to be able to do that and authenticate anything logging into it. While those do exist, retrofitting it or putting it into existing software is probably the bigger hurdle. We use AWS quite a bit, and they do offer services like that. But now you have to put that into every single service you have or application that you have, and that takes time. How long will it take? we're obligated. I believe the DoD's timeline for zero trust is in the next 2 years. So it will take that long. I believe that over time they've moved it out, but right now I think they're going to stick to zero trust in 2027. And then prior to this, you also have CMMC, which isn't zero trust, but they kept moving that out as well because it was hard to comply with CMMC. So there is this pattern in the government where they start to move things out as they recognize that they're very difficult. So zero trust, 2 years is I think where it's going to happen.
Okay. I think we're going to have to make this the last question. Any of we've missed out, we'll follow up afterwards. When ground stations need to be refreshed, are you looking to refresh with legacy parabolic antennas, or is there a push to move to AESAs or a combination of both?
So it's wherever the market drives us and wherever the capability is. Active electronically scanned arrays, we're definitely open to looking at it. One of my colleagues actually answered this question and he's spot on. But what I'll add to this is the importance of having an architecture that is about the data management, about providing data to the customer over here and using the best technology on the back end where our customers aren't aware of what's going on underneath. That's where this comes in. When new technology comes out that works extremely well, is proven, and is production ready, we can adopt that new technology. We can, with the virtualized ground systems, we can decide where we want to put the modems and the RF chain, and then we can deliver that data to the customer. Now, the customer doesn't need to care if it was an AESA, if it was a traditional parabolic, if it was optical, they just need their data streams. And so having that architecture that abstracts that away is really important. The cost of some of these has always traditionally been a problem. I've seen a lot of promise in phased arrays in general for delivering multi-band, multi-customers or multi-satellites at the same time. You've got Northwood out there, and I think they're probably doing something different. They're going to be successful, but these things take time, and we need to know that they're TRL-9. We need to know that they're ready before we start adopting them. So we keep an eye on all ways to speak to space, so to speak.
Well, gentlemen, our time is up. I'd like to thank both Matt and Brad. It's been really informative. Learned a lot about software ground segment, learned about the challenges, how you're adopting, how you're facing them. Very interesting. I'd also like to thank the audience that's taken the time to join us today. So with that, I will say goodbye and thank you very much for joining us.
Thank you.
Thank you. Yeah.
Thank you.